Welcome to module 2 of chapter 2. In this module, we will show number of primes are infinite. We will see different proofs for the same. The first proof is due to Euclid. It is believed that this is the first proof proved by using method of contradiction. Then we will introduce Euler products and Riemann zeta function. Finally, we will look for arithmetic progressions which contains infinite number of primes. In this module, we will see there are infinite number of primes. Objectives of this module are different proofs for primes are infinite, Riemann zeta function and Euler product, infinite number of primes in arithmetic progression. First theorem, there are infinite number of primes. This proof is due to Euclid. Suppose there are only finite number of primes, say p1, p2 and so on pk. So, we are proving this by method of contradiction. So, let us assume let p equal to p1 into p2 and so on pk plus 1. Then by fundamental theorem of arithmetic, p has a prime factor. Since p first prime p1 is at least 2. So, p is greater than or equal to 2, capital P is greater than or equal to 2. So, it has a prime factor. So, if that prime, if you take it as a pi, small pi, pi divides p for I 1, 2, 3 and so on k, that is this pi is 1 among p1, p2 and so on pk, then what is going to happen is this pi also divides pi minus 1. It is because pi minus 1 is nothing but p1 into p2 and so on pk. Since pi divides pi minus 1 as well as pi divides p, hence pi divides 1. So, this is a contradiction. So, prime dividing a number 1, but by fundamental theorem of arithmetic, p has to have one prime divisor. Hence, above prime that pi does not work. So, there exists another prime which is different from p1, p2 and so on pk. So, this result is saying that if you choose any finite number of primes, any set of finite number of primes, then it is possible to produce another prime which is not in that set. So, this shows that there are infinite number of primes. The numbers of the form p1, p2 and so on pk plus 1 are called Euclidean numbers. The way which we created the capital P, those numbers are called Euclidean numbers. So, that means that kth Euclidean number is equal to product of first k primes plus 1. Let us denote Pn be the nth prime number, means nth prime number means in the usual numbering, that is in the natural numbers 1, 2, 3 and so on n. So, Pn is denote the first nth prime number, and we denote En is equal to p1, p2 and so on Pn plus 1. Then it is easy to see that E1 is equal to 3, E2 is equal to 2 into 3 plus 1, that is 7, E3 is equal to 2 into 3 into 5 plus 1, that is equal to 31. E4 similarly we can calculate, that is actually 2 into 3 into 5 into 7 plus 1, it turns out to be 211. Similarly, E5 is 2311. So, all these are prime numbers, but if you calculate E6, that is equal to 59 into 509, this is not a prime number. So, all these numbers, Euclidean numbers, need not be prime. Similarly, one can easily check that E7 and E8 are also not primes, but these numbers have interesting property. It is a nice exercise to check that each of them is of the form 4k plus 3. Hence, none of them is a perfect square, as we proved that every perfect square is of the form either 4k or 4k plus 1, but all these numbers are of the form 4k plus 3. That is why none of these are perfect squares. Also, Euclid proof of infinitude of primes provides an estimate for nth prime. If Pn plus 1 is n plus 1th prime, then we know that Pn plus 1 is less than or equal to En. that means En has to divide a prime which is other than P1, P2, Pn. So, the Pn plus 1 should be less than or equal to P1, P2 and so on Pn plus 1. So, if you replace P1, P2 and so on Pn minus 1 by Pn, then clearly this is less than or equal to Pn power n plus 1, but this is a very crude estimate, that means we can improve this further. In fact, by induction we can prove that Pn plus 1 is less than or equal to 2 power 2n minus 1. This is also very bigger bound, actually we can improve further. So, Euclid's proof not only showing the number of primes are infinite, but is also giving estimates for the primes. Now, we look for another proof. Of course, this imitates the proof of Euclid's proof. In this case, we will assume that B1 is equal to 1 and B2, B3 and so on are defined by a recurrence relation, that is Bm plus 1 is equal to B1 into B2 and so on Bm plus 1. It is same way as we defined capital P in the proof of Euclid's. So, now then by definition, if you take both m comma n greater than 1, then what is going to happen is Bm is equal to Bn into y plus 1. It is because Bm is equal to B1 into B2 and so on Bm minus 1 plus 1. So, Bn will be one of the quantity. So, Bn into remaining, that is B1 into B2 into and so on remaining quantities up to Bm minus 1, will if you call them as a y, then Bm is equal to Bn into y plus 1. Now, if you take the GCD of these two numbers Bm and Bn, if you assume D is the GCD of Bm comma Bn, then D has to divide Bm as well as Bn. So, D has to divide their integer linear combination, that is D has to divide Bm minus Bn into y, that is equal to 1. So, D has to divide 1. So, the GCD of these numbers is 1, that is both Bn comma Bm have different prime factors. That means, the prime factors of Bn and prime factors of Bm are different. There is no common prime factor for Bn as well as for Bm. So, what it shows? It is easy to see that these numbers for giving different values for m there Bm plus 1 is equal to B1, B2 and so on Bm plus 1, we can get infinite numbers, but each number the prime factors are different. We have infinite numbers, each number have different prime factors, that shows that there are infinite number of primes. So, in this proof also, though we imitated Euclid's proof, but the advantage that we are not proved by using contradiction. Now, we will see another proof. For that we use the following result. It is well known to you, the harmonic series, that is denoted summation 1 by n, that is n is equal to 1 to infinity 1 by n, that is diverges. So, how to show this result? So, if you take 1 by 3 plus 1 by 4, it is easy to see that 1 by 3 plus 1 by 4 is greater than or equal to 1 by 4 plus 1 by 2, that is equal to 1 by 2. Similarly, if I take 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 2 1 by 8, then it is greater than or equal to 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. It is because 1 by 5 is greater than 1 by 8, 1 by 6 is greater than 1 by 8 and so on. So, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is also greater than or equal to 1 by 2. In fact, it is strictly greater than 1 by 2. More generally, if I take m equal to 2 power k minus 1 plus 1 to 2 power k summation 1 by m, then this is greater than or equal to again 1 by 2. That means, hence what we have here is summation 1 by n can be written as 1 plus, if you regroup like this, that is summation 1 by n is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 as one group, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 as another group and so on. Then it is greater than 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, we proved it is greater than 1 by 2. Similarly, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is greater than 1 by 2. So, all of them are 1 by 2, 1 by 2 and it is going to be infinity. If you need, you can do further calculation, that is 1 by 2 plus 1 by 2 is again 1, 1 by 2 plus 1 by 2 is 1. So, 1 plus 1 plus 1 plus like that infinite times. So, we are going to get infinity. So, this is not a complete proof, but this is sketch of the proof. So, with this we understand that the harmonic series summation 1 by n diverges. For this harmonic series diverges, we will give another proof, alternating proof. So, another proof for divergence of harmonic series. Let us consider S is equal to 1 by 2 plus 1 by 3 plus 1 by 4 and so on. That means, in the harmonic series just we not took first term, that is 1. So, by using the identity 1 by n is equal to n minus 1 by n minus 1 into n, if we can write this as 1 by n minus 1 into n plus 1 by n minus 1 into n plus and so on 1 by n minus 1 into n minus 1 times. We can rewrite S as S equal to 1 by 2 plus, that is the first term of the series which we started. Then 1 by 3 can be written as 1 by 6 plus 1 by 6. It is because we saw that 1 by 3 is written as 1 by n minus 1 into n plus 1 by n minus 1 into n and so on 1 by n minus 1 into n minus 1 times. So, if I take n equal to 3 in that equality, so 1 by 3 is equal to 1 by 3 minus 1 into 3 plus 1 by 3 minus 1 into 3. So, 2 times, that is 1 by 6 plus 1 by 6. Similarly, 1 by 4 can be written as 1 by 12 plus 1 by 12 plus 1 by 12. In the similar manner, 1 by 5 can be written as 1 by 20 plus 1 by 20 plus 1 by 20 plus 1 by 20. This will continue like this. So, what we can do now is, this sum can be written as S1 plus S2 plus S3 and so on. What is S1 here? S1 here is that 1 by 2 plus 1 by 6 plus 1 by 12 plus 1 by 20 plus and so on. That means, I am taking 1 by 2 first term in each bracket, that means 1 by 2 plus 1 by 6 in the second bracket and 1 by 12 in the third term and so on. S2 is equal to 1 by 6 plus 1 by 12 plus 1 by 20 and so on. S3 starts from 1 by 12 plus 1 by 20 and so on. So, this S1 plus S2 plus S3 and so on, this is also we have infinite number of terms. First term is S1, second term is S2, third term is S3 and so on. So, now by using 1 by n into n minus 1 is equal to 1 by n minus 1 minus 1 by n, we can prove that S1 is equal to 1 by 2 plus 1 by 6 plus 1 by 12 and so on, it is equal to 1. With a little calculation we can prove this. So, but for that we need to use that 1 by n into n minus 1 is equal to 1 by n minus 1 minus 1 by n, this is by telescopic sum. Similar to this result we proved for triangular numbers. So, one can refer those slides. Now, similarly, S2 is equal to 1 by 6 plus 1 by 12 plus 1 by 20 and so on, this is equal to 1 by 2. Here it is easy to see, if you look at S1, if S1 is equal to 1, then you look at S1 and S2, the only difference S2 minus S1 is equal to, or S1 minus S2 which is equal to 1 by 2, S1 minus S2 is equal to 1 by 2. So, we have to subtract half from S1, then we will get total sum of S2. Similarly, S3 is easy to evaluate, S3 we will going to get 1 by 3. So, in this way S4 becomes, we are going to get 1 by 4 and so on. So, but we have that. So, finally, we will get S equal to S1 plus S2 plus and so on. So, we will get S is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. That is, actually we started S as 1 by 2 plus 1 by 3 and so on, but now we got S is equal to 1 plus 1 by 2 plus 1 by 3 and so on. That is what we proved is S is equal to S plus 1. This is not possible for a finite quantity or a convergent series. So, this is a contradiction unless S is divergent. So, obviously, S plus 1 is also divergent in that case. So, this is a alternating proof for harmonic series is divergent. So, now we will go for proof for infinite number of primes. Actually, we are giving different proofs for to show there are infinite number of primes. Earlier we given 2 proofs, now we will use the harmonic series is divergent to give an alternative proof. For that again we need few more details. For that the first one is, let P be a prime number, then we know that 1 plus 1 by P plus 1 by p whole square and so on is equal to 1 by 1 minus 1 by p. So, it is because of geometric series 1 plus r square and so on. Whenever r is mod r is less than 1, then this is equal to 1 by 1 minus r. Here r value is 1 by p. So, 1 plus 1 by p plus 1 by p square plus 1 by p cube and so on, that is converges, and its value is equal to 1 minus 1 by p whole power minus 1. So, this actually you can extend it. If assume s is greater than 1, then 1 plus 1 by p power s plus 1 by p power s whole square and so on, that is also converges. It converges to 1 by 1 minus 1 by p power s. So, with this we will go for we will introduce Euler product. Euler stated the fundamental theorem of arithmetic in terms of harmonic series. It is one of the beautiful equation Euler found. So, he expressed the fundamental theorem of arithmetic as a sum is equal to product, that we will see now. This is called Euler product. Because of Euler product, many new functions were introduced, such as Riemann zeta function, Dirichlet function, etc. So, Euler product is defined like this. Here the symbol is zeta, zeta of s is equal to summation 1 by n power s, this is equal to product p is a prime 1 minus 1 by p power s whole inverse. This is what we call Euler product. If you look at here, one side we have a summation 1 by n power s which is equal to the product. So, now we will discuss about the proof of this Euler product. We are not giving the complete proof, just we will look at the sketch, just an idea how they are equal. Zeta of s is equal to summation 1 by n power s. So, if you expand it, it is nothing but 1 plus 2 power s plus 1 by 3 power s plus 1 by 4 power s and so on. So, we are saying this is equal to p is a prime 1 minus 1 by p power s whole inverse. So, it goes like this. So, why these two are equal? So, if you expand it, for example, you know the first prime is 2. So, we will get 1 plus 1 by 2 power s plus 1 by 2 power s whole square and so on. Next prime is, now we have to multiply it. Okay. The next prime is 3. So, we will get 1 plus 1 by 3 power s plus 1 by 3 power s whole square and so on. Immediate next prime is 5. So, that the product continues like this. So, it is a products like this, but each is a sum, each is an infinite sum. So, how to show these two are equal? We are not showing, but we are just observing few things. If I take 1 in the summation 1 by n power s 1 there, if you look at 1 can be obtained by multiplying 1 into 1 into 1 into, from each sum I will take the first term, then if you multiply I will get 1. So, the next one is, let us look at 1 by 30 power s. 1 by 30 power s can be obtained by multiplying 1 by 2 power s, 1 by 3 power s and 1 by 5 power s. Similarly, one can check 1 by 80 power s. Actually, these are equal because of the fundamental theorem of arithmetic. Every number greater than 1 can be expressed as product of primes. Because of that, it is easy to see Euler product is true. Now, we will utilize this to show that number of primes are infinite. How can you use that one? Let S belongs to C, a set of complex numbers, then the function zeta of s is called Riemann zeta function. First, Euler actually defined this function for S is for real numbers. Riemann extended this function for complex numbers. It is easy to see that zeta of 1 is a harmonic series, that is zeta of 1 is equal to summation 1 by n, which is equal to, by Euler product, this is equal to product of all primes 1 minus 1 by p whole inverse. So, now if the number of primes are finite, then what is going to happen? On one side we have finite quantity, in other side that is summation 1 by n, that is going to be infinity. So, these two are not going to be equal. So, this shows that their number of primes are infinite, that is, we will repeat. Consequently, if the number of primes are finite, then the product P is prime 1 minus 1 by P power s is a finite quantity, whereas zeta of 1 is an infinite quantity which is divergent. So, this shows that the number of primes are infinite. It is another proof. Though Euclid proved simple proof for number of primes are infinite, but this proof cannot be generalized to show number of primes are infinite for any arbitrary arithmetic progression, but Euler products can be generalized. This is one of the best example to understand why we need different proofs for the same problem. Now, we will see Dirichlet theorem. It says that if A and B are relatively prime positive integers, then the arithmetic progression A plus B, A plus 2B and so on contains infinitely many primes. So, if I take A equal to 1 and B is also equal to 1, that is in that case we will get 1 plus 1 comma 2 comma 3 and so on. So, that is usual number system, that is 1 2 3 natural numbers. We already proved that it contains infinite number of primes, but this result now Dirichlet extended to any arbitrary arithmetic progression, but only condition is that A and B should be relatively prime. It is not true for any arbitrary arithmetic progression. Let k be a positive composite number, then the arithmetic sequence 0, k, 2k, 3k and so on contains no prime number. So, this is the reason we need A and B are relatively prime in Dirichlet's theorem. The set 2k plus 1 contains all primes except 2. 2k plus 1 is nothing but a set of all odd numbers. So, it contains all primes except 2. The number of primes of the form 4k plus 3 are infinite. Now, we will see proof of this result. That is, first we note that the product of 2 or more integers of the form 4n plus 1 is of the same form. That is, let k1 equal to 4n plus 1 and k2 equal to 4n plus 1, then k1 into k2 equal to 4n plus 1 into 4m plus 1, which if you simplify it, we are going to get 4 into 4m n plus m plus n plus 1, that is again it is of the form 4k plus 1. So, we will use this in the proof. So, next let us assume that q1, q2 and so on qk be the only finite number of primes are of the form 4k plus 3. So, again here we are imitating the proof of Euclid's. Here it will work for this arithmetic progression, it is possible to extend Euclid's proof. Consider m is equal to 4 times q1 into q2 and so on q1 minus 1 plus 3, then by our construction qi is less than m for all I lies in between 1 and k. Let m is equal to p1, p2 and so on pr for some r be the prime factorization of m. Since m is odd, every pi will be of the form 4m plus 1 or 4m plus 3. Further, m is of the form 4m plus 3. So, at least one of the primes, say pt is of the form 4m plus 3. It is because if all the primes are of the form 4m plus 1, then their product is also of the form 4m plus 1, but m is of the form 4m plus 3. So, one of the prime is of the form 4m plus 3, but we have only finite number of primes of the form 4m plus 3 q1, q2 and so on qk. So, pt is to be equal to qj for some j, which gives a contradiction as pt divides q1, q2 and so on qn, and also pt divides 4 into q1, q2 and so on qn minus 1. That means pt divides 1. So, which is a contradiction. That is why there are infinite number of primes of the form 4m plus 3. So, now we will ask few questions. Does there exist an arithmetic progression such that all of its entries are prime? The answer is no. We will prove by contradiction. Let us assume every term in the arithmetic progression is a prime, that is a plus d, a plus 2d and so on, every term is a prime. In particular, if you let a plus nd is equal to p is a prime number, then if you consider n plus Kp plus 1th term of this progression, which is equals to a plus n plus Kp into d, which is equal to a plus Nd plus Kp d, which is equal to p into 1 plus Kd. That means, this term of the progression is divisible by p. So, that means, this is not a prime. So, it is difficult to have arithmetic progression such that every term in the arithmetic progression is prime. But what we can say about arithmetic progression? Now, we will ask some other questions. Before that, it is better to observe few things. Any single prime is an arithmetic progression of length 1. 1719 is an arithmetic progression of length 2. 357 is an arithmetic progression of length 3. 5, 11, 17, 23, 29 is an arithmetic progression of length 5. So, these questions, this leads to following question: are there arithmetic progressions of arbitrary large length consisting only primes? We already proved that there is no arithmetic progression such that each term is a prime of with infinite number of terms. But now we are asking, is there an arithmetic progression of arbitrary large length? Now it is finite, consisting only primes. Or asked above question, more specifically, given a number k, can we find a comma b belongs to n such that the set b, b plus a, b plus 2a and so on b plus n a, where n is greater than or equal to k, contains only prime numbers? The answer for this problem is yes. This is known as Green-Stoy theorem, but here we are not proving this result. So, now we will see Goldbach conjecture. This is one of the oldest problem in number theory, still proof is waiting. It says that every integer greater than 2 is sum of 2 primes. So, this problem is still open. This is one of the beauty of number theory. Here you can see that this is easy to understand, statement is very easy to understand, and people also tried to prove this one, and it is proved for billions of integers. First, it is true for first billions of integers, but still we are not proved for general. So, still it is a conjecture. So, Goldbach conjecture is also equivalent to. So, people try to prove this one. So, they will convert this problem into equivalent other problems. For example, this is equivalent to every integer greater than 5 is sum of 3 primes. If you prove this result also, Goldbach conjecture is true. The proof for this problem, this equivalence is, it is easy to see that 2n minus 2 is equal to p1 plus p2. If the Goldbach conjecture is true, then we can write 2n minus 2 is sum of 2 primes p1 plus p2. So, 2n is equal to p1 plus p2 plus 2. So, 2 is a prime number. So, we have sum of 3 primes. Similarly, another thing is, another equivalence is, each odd integer greater than 7 must be sum of 3 odd primes. So, here also proof is simple. Let n greater than 7 be an odd integer, then n minus 3 is even and greater than 4. So, by Goldbach conjecture, n minus 3 is sum of 2 odd primes. In this module, we proved there are infinite number of primes, and we proved this by using different proofs, and we also stated Dirichlet's theorem, but we not proved. This proof requires a lot of machinery. It is believed that this is because of this proof, a new branch called analytic number theory is emerged. With this, we will end this module.